Hey everybody, Dr. A here, and in this video we're going to be providing some background information on a phenomenon known as creep. So let's go ahead and get into it. So creep is the time-dependent permanent deformation due to long-term loading. Now, the key phrase in this first sentence is time dependent, okay? So far in our study of material behavior and mechanics of materials, we have not really talked about the time dependency of the material behavior and the development of material properties. We have really just talked about you apply a load, or maybe you change the applied load, or you take the applied load off, but we've not actually talked about the time essence of how long a load would be present on a specimen or in a system before it starts changing the behavior over a certain amount of time. So this is the concept of creep. We are incorporating this idea of time dependence while loading. Okay, so let's keep digging into it. It turns out that a component of a system that will sustain a load for a long period of time may be designed to resist a specified creep strain for the designed time. So let's say that we have a component of a system that we're interested in, and maybe that component is going to have a load on it for a really long period of time. And so we're going to need to figure out how that long duration of the load being present is going to affect that particular component, okay? So that's when we start getting into this idea of creep strain, all right? So for example, steel bolts are often or sometimes designed for a creep strain of 0.1% per year. So what that means is, when we say strain, we're talking about epsilon. So if we're saying a creep strain of 0.1% per year, what we're meaning is sometimes bolts are designed to basically experience 0.1% of strain or 0.001 strain per year, okay? Because maybe those bolts are subject to a load that's just going to sit there for a long period of time, okay? Now, creep strength of a material can be determined by loading different specimens of that material with different axial loads and measuring the length of time that each specimen reaches that creep strain. Okay, so let's turn the page and think about that. Let's call this term epsilon creep, and we'll call this the defined creep strain. And again, it could be anything. We said for steel bolts, we might use 0.1% per year, but this could be anything for any material or any component or system, okay? And so what we can do then is take several specimens, okay? We're going to take several of these specimens, all made of the same material, okay? However many we need. I'm just drawing a bunch of them here. Let me draw that last one a little bit better for us. Okay, however many we need. I'm just going to put 4 here for now. And let's say that we have, we put a load here, P1, on the first specimen. And then we put a different load, P2, on the next specimen. And then a different load, maybe P3, and so on. Let's call this P4. And let's say that, P1 is less than P2, is less than P3, is less than P4. So what we're saying is each one of these specimens, each of these loads, P1, 2, 3, 4, is getting bigger compared to the previous load, okay? And so we test all these specimens, and we basically hang these loads on each of these specimens for as long as it takes until we reach epsilon creep. So let's write that down. We're going to say allow loads P sub I to remain on specimen until each specimen reaches epsilon creep in terms of that defined creep strain, okay? And so what will happen? Well, will they all reach epsilon creep at the same time? No, they won't. In fact, they will all be different times, and that time to reach epsilon creep for each specimen is going to depend on the magnitude of each of these loads hanging out here, okay? And so they all will eventually get to epsilon creep, but each one will take a different amount of time, okay? So let's say that, to reach epsilon creep, this is like, T1, T2, T3, T4. So I'm going to say, T sub I is the time for each specimen to reach epsilon creep, okay? Now, you tell me, maybe you should pause the video and answer this question for yourself, but what order will they reach epsilon creep in? Which specimen will reach epsilon creep first, second, third, or fourth? Maybe pause the video and say it to yourself because I'm about to tell you, okay? Well, the larger magnitude load, the specimen with the larger magnitude load, in this case, P4 has the largest magnitude, that will reach epsilon creep the fastest or the soonest, right? Which makes sense, okay? So if P4 will reach epsilon creep the fastest, what does that logically tell us? That tells us that the higher the load is that is hanging or being applied to this component for, quote, a long period of time, the higher the magnitude of that load, the faster or sooner that specimen will reach the creep strain, okay? And so if I were to write this mathematically, what will these times look like? Well, T4 will be the shortest time that epsilon creep is reached. So we'll say T4 less than T3, less than T2, less than T1. Now, I can develop a plot of this. I can plot this relationship. So I'm going to form a set of axes like this, and I'm going to call this vertical axis stress. And, of course, stress is just, P over A, okay, in this particular case, because we're dealing with axial loads. And this horizontal axis will be the time, and this time could be hours. It doesn't have to, it could be hours or days or weeks, whatever the experiment is. And so what'll happen is that you're gonna have let's color code this at that first loading, P1, T1 will be the slowest, right? So that'll be maybe somewhere out here, okay? And then at a bigger load, P2, then T2 will occur a little faster, a little sooner. Maybe it's like right here, for example, okay? And then at a bigger load, P3, that'll again happen a bit faster. And then at an even larger load, P4, that'll happen even faster. So what we'll get is this kind of nonlinear relationship, okay? You'll get this curve that looks something like this. Not my best curve, but you'll get this curve that passes through the data, all right? And so again, this right here is what? This is T1 and P1, and then of course here this is T2, P2, this is, I'm gonna put in parentheses here, T3, P3, and then this highest point all the way on the left is gonna be T4 and P4. Okay, so again, the larger load will reach that creep strain in a shorter amount of time. Okay, now why is this important? Again, in engineering and all forms of engineering, especially applications in civil and mechanical and even biomedical, maybe aerospace engineering, you're going to have components of things that you're designing that have to sustain a load for a long period of time. And you might need to do a creep analysis. Now, not every situation of design will need a creep analysis, but some will, especially small components that maybe have very small cross sections, or components made of materials that are maybe not very strong for some reason. Maybe you have a polymer material that is supporting a large load for a long period of time. So you might need to look at creep data for the material that a particular component is made out of, just to make sure that when you put that long-term load on your system, that you're not going to have a creep failure that is unexpected, or a creep failure that causes another part of the system to not behave like it's designed to. Okay, so that concludes this video on background information on this kind of creep analysis concept. This is really meant for to be an introduction in either a mechanics of materials class, or a material science class, or even maybe a structural analysis or mechanics course. So this is not, by any means a comprehensive video. So hopefully you found this short little intro video on this topic helpful. If you did, please hit like and subscribe, and be on the lookout for other content like this. Thanks for watching.